What's up, everyone? Welcome to week 119, building my own operating system. Thanks a lot for joining. As usual, here's the map. And so I'm doing these 3 pre-recorded streams. And here's the viewing order if you really want to watch it in chronological order. That's just how it works when I pre-record things. And so tomorrow will be week 116, containing all the progress, which hasn't been released yet. But then we'll in the next couple weeks. So this is going pretty well. In the last 2 streams, I've been working hard on smart pointers. I want my task struct to have a smart pointer to its stack memory, which it is responsible for deallocating when the task is destroyed. So this is a pretty natural application of a smart pointer. And in week 117, we explored manually writing one from scratch, although it was like kind of incomplete. It demonstrated the concept. Then in week 118, I was working on not doing it from scratch, but rather reusing the smart pointers in the various libraries that I have available to me. And I learned something kind of interesting. And so at first, I was trying to use a stud unique pointer, like the classic one from the STL, which I have access to. And I thought that wouldn't work, but I thought that wouldn't work. That was actually wrong, but because of that, I went and moved on to FRIG and got it working with FRIG, and then realized I actually could get it working with standard unique pointer, stud unique pointer. And then lastly, I realized ETL also has a unique pointer that is extremely similar to stud unique pointer. And the actual very cool part is the ETL unique pointer is a drop-in replacement for stud unique pointer. And so things just totally build. I can just swap between either of these, and it just builds. And so that's pretty cool. And I was considering what to do, like which of these should I use? So my preference in general has been to, like, the order is, if it's in stud, like STL, use it. Otherwise, if it's an ETL, use it. Otherwise, if it's in FRIG, use it. And that's sort of been the policy. I have a bunch of this ETL stuff anyway, so I was wondering if an ETL unique pointer would be good, but in the end, I decided that no, I'm going to stick to my policy. Stud unique pointer first, then ETL, then FRIG. Main reasons being, so first off, stud is, I'm using libstud C++ from GNU because libc++ from Clang apparently is not working for freestanding as easily as libstud C++ is. And Minsky from Limony has packaged libstud C++ into a nice freestanding CXX headers project, which I'm currently using. So, but the benefits and the reasons are stud, this one is most likely to be best tested and least buggy. Also, if other people want to work on this project, the semantics of stud unique pointer are quite well known to any C++ programmer, whereas ETL and FRIG are much more niche. And so by going with that first, it makes it easier for other people to work on the code base. It's also reducing surface area for bugs. ETL is next because that is the next most commonly used library. I'm using it pretty extensively for my static containers all throughout the scheduler so far, and in my tasks and stuff like this. Where is it? I think right here we can see I have my ETL pool. I have my task list, which is an ETL list, and so that's a little bit more pervasively used than FRIG is, and that is my second option. Another reason to not use ETL unique pointer, even though it works, is because it might suggest that there is some specific reason that the ETL unique pointer is necessary as opposed to the stud unique pointer, when in fact that is not true. And so I don't want to imply anything about the fact that I'm using ETL unique pointer. It's just a drop-in, and so by not using that, it helps clarify that there's no particular special reason about that. And then lastly, FRIG is the last in line because it is, from my understanding, the least well tested, it comes from the hobby scene, the hobby OS scene. I have run into some bugs with it that I patched personally. I mean, there's also issues with ETL. I understand ETL has a little bit more industrial use than FRIG does. So for that reason, it's last in line, but it does have cool stuff that is not available in any of the others, such as its formatting functionality. And so I'm using that for the logging. I'm using FRIG format for that. So they all have their place. They all supply different things, but I have a certain pecking order in which I am using them and prioritizing which to use. It is a little bit confusing that there's so many libraries here, but that's, yeah, there's reasons for all of them, and that's just how it is. And so yeah, so this is like pretty much the final state of this header in its cleaned up form. Again, so messy whip commit history, I'll clean that up later. And that's pretty cool. That's bringing us to a pretty good state. So now we have not only like working, a basic form of working cooperative multitasking, but the implementation is actually looking pretty good too. And I'm pretty proud we have, we have a pretty nice implementation. I think it's pretty clean. It's probably missing stuff, it's pretty simple, but we have a nice software engineering separation of concerns. The policy is separate from the scheduler. We have extra effort spent on doing, on like correctness, on making sure we destroy the task in a deferred manner. And so we're not destroying the task stack while we're still executing on it, for example. So we have deferred task cleanup. That is pretty nice. And then we now have some cool shared pointer, smart pointer stuff going on, which allows us to clean up the task stacks. So there's a couple things on the menu for today that we could work on. So one is the idea, I'm calling it the big blob. Another idea is, I'll call it pre-init stack guard pages, unmap them. And you know what, I'm not quite sure how I want to go about doing this. I think I'm thinking that probably the guard pages will be the first task of today. So we'll just clear out the cloud. We're not using that right now. So here's what I'm talking about. In our task struct, we currently the task runs some code in its constructor to initialize itself. The most prescient part of that is setting up its stack with a landing pad in case the task ever returns from its function without calling the exit API. Another small thing that it's doing is that it's unmapping the guard page. And that's just here because that was just sort of an easy place to put it when I was prototyping this. And I would still say I currently am in the process of prototyping. But there's a couple problems with this. And so it's kind of the wrong place for this to happen because it's kind of wasteful. And so the way the task stack pool, the way the stacks work on my system is, first of all, I'm statically allocating everything. And so I'm reserving large regions of memory up front for a fixed number of tasks to run. And then I'm reserving a fixed regions for their stacks all up front. So this is not really dynamic allocation, or it's a bit of a hybrid approach because I'm using this task pool. or a task stack, this pool of stacks. But anyway, there's this fixed number of task stacks that exist, and the task stack is this struct that looks like this, which has a guard page followed by an actual stack page. And I'm aware that this is probably too small for a stack. It's just one page, but we can increase that later. And that is how things are laid out. And then when it's time to create a task, we allocate one of these from the pool and then construct a unique pointer from it and pass it into the M tasks. And construct the M tasks, construct a task and pass it to this task. And then the task takes a V address space, which it does not store, it just takes one so it can make sure that the guard page is not mapped. But the thing is, after a while, all of these task stacks will have been used and then kind of recycled. And after the first, n iterations of a task starting and exiting, all of these guard pages will have been unmapped from the kernel's address space. And so it is, from that point on, it is unnecessary to do an unmap. And this operation involves doing page table stuff. It is, I don't know, it's like not necessarily so, it's like not expensive. It's not that expensive, but it's also just why there's no reason to do it redundantly for like the whole lifetime of the OS if we don't need to. So a better way, maybe a different way, probably it's better, is to, on initialization of the kernel, just pre-process all these guard pages and unmap all of them in like one swoop. And then from that point on, any task can assume that its guard page has been unmapped from the address space. And this is probably the better way to do it, because then we just eliminate all of this from the responsibility of the task. And even one other benefit is technically this code should actually be doing an inval page or something like that, or like, I mean, clearing the TLB is like a little bit much, but an inval page to really like apply this change to the page tables. I'm not even doing it right now, so it's like kind of incorrect. The only reason it was like kind of working is because when I was testing this, I was manually reloading CR3, which is also a bit of like the nuclear option. But that I was doing it kind of externally, and ideally, if the task was even responsible for this, it should be responsible for handling every part of the process, including like unmapping the page, but then also doing the inval page instruction to invalidate the TLB. And so by removing this, it really simplifies things, and I think it's a bit better from a design perspective. And so this will be the warm-up for today's session, but the idea is, how do we do this? At what point would we initialize these things, or what? And I think actually this is going to be pretty easy. I'm just gonna wipe and get a clean scheduler HPP, get a clean working area. And I think the obvious place for this is in the constructor of the scheduler. And so like I was saying, we have this pool and it gets constructed, but then we want to do some further customizations or tweaks, and it makes sense that this happens in the construction of the scheduler. So I'm gonna make a function in the private section, probably at the bottom right here, and I'll say unmap guard pages, and the AI is so eager to help me at the slightest hint of anything. And so I'm going to try to use my brain a little bit without seeing the answer, but that's sort of the approach on map guard pages. We're going to call that in here. And it's kind of interesting because look at this pool. And so we need to, it's basically gonna, we need to go through every single page in the pool or every single task stack in the pool. And in order to access it, I think we need to kind of like allocate. I mean, this is actually kind of an interesting question, and it even challenges my initial assumption. So the idea is like, let's say we have, right now our pool is super small. It has 4. We only have 4 tasks, and yeah, so the idea is like we need to go and allocate each one, unmap, and then free them all back to the pool. And then we can do like an inval page for each one of them, or we can, I don't know, but that's just a bunch of upfront work that, like, it sort of seems like not a lot of work with our tiny play kernel, which only has 4 tasks. But imagine if we had 4,000 tasks or something. Then we're introducing this, we're introducing this just delay to the boot process. And maybe I'll write down some options. So one, init all on boot time to have the task do it on CTOR, and like some pros and cons. So pro, con. So pro is simple, task doesn't need to do anything, slightly more efficient. Con is adds delay to boot up. And then sort of the opposite. So the advantage of doing it in the CTOR is that there's no boot up delay. We are doing it lazily as tasks are created, which is kind of an interesting idea. The downside is at some point it will be wasteful after all task slots have been used and all guard pages have been unmapped. It's redundant to keep unmapping them. And so there's this tension between doing it lazily and just in the simplicity of just doing it up front. And I wonder if we can do some brainstorming about how to even be smarter here. Like, you could imagine some flag counter that tracks how many tasks have been created, and then after n max tasks have been created, we no longer need to do this. But this actually doesn't even work, because let's just say, so the idea here is like we have for 4 things, and then we just keep track of like, okay, this thing was used, and this thing was used, and this thing was used, and then this thing was used, then this thing got recycled, and then now on this time, we know that all 4 of them had been used, and their guard pages were cleared, and so this new guy doesn't need, it knows that all of them must have been cleared, and so it doesn't need to unmap, and so there's like some kind of if statement in the constructor of the task. But the reason this is broken is because you can have like pathological scenarios where it's like, let's say this task starts, then this task ends, then this task dies, and another one comes in, and this task dies, and another one comes in. So that's already 4, but these 2 have not even been used at all yet. And so then a simple, like that simple counter is like just doesn't work, because then if we were doing that simple counter, it's like, okay, then this one finally comes along and gets used, and it thinks, oh wow, since 4 tasks have been created, I don't need to unmap my guard page, but that's not at all true. So so just taking, I mean, it's probably, I mean, it's like a little bit slow. I mean, like that's just something that is going to slow down boot up time, and this would be one of the yeah, this would, this thing will cause like a linear, I mean, it linear slows down sort of. I mean, it depends on what other things are in your boot sequence, but the more tasks there are, the longer it's going to take. It's linear time. So I don't know. There could be a flag or something in each of these. But even still not, there could be a flag that stores whether it has been cleared or not. Which, so the naive way to do it wouldn't work, but the naive way would be to add like a bool to the task stack, or like, I don't know, reuse some weird bit in the task stack. And then that's going to mark whether it has been set or not, and then the task can know whether to do it or not. But the reason that doesn't work is because these things from the pool, like based on the way the pool thing works, these are like created and destroyed, and so state does not really linger between, like there isn't really like a piece of state corresponding to the task stack that lingers for a long term period of time. And so if we wanted to do that, we would need to have some separate state, I think. And so the way it would work is like, we have our tasks, our task stacks, and we have off to the side, we have like, for every single task stack possible, we have a bit or a bool or something corresponding to each one of these. And every time we activate a task and prepare and unmap the guard page, we then set this to 1 over here. And then I guess there's a few different ways. And so one thing is like the task itself could be checking this bitmap, and then it sees, okay, I'm using the first task stack. Okay, let me see, do I need to unmap it? This thing, no. You check the bit, okay, no, it was already unmapped, so I don't need to do that. But then it's like, okay, I'm using task stack number 4, and do I need to unmap the guard page? And it's like, oh, this thing has never been unmapped yet. Yes, I need to do that. So that would again be some kind of like if statement here, and we would need to have address space here. We would need to do the inval page thing. We would also need to get past a bitmap to do the checking, and yeah, what we get out of that is just we get some optimization. We get this a bit lazier way of booting up, and we don't incur this sort of like this just very simple linear boot in it. And after talking it through like this, I mean, this is a reasonable approach, but it is an optimization, and I think I want to avoid optimizations right now. We don't like the boot. It's not like the boot time is like slow. And this is always something that we could do later. And I think it has an impact on the complexity. And I'm also trying to reduce complexity when I can. I'm trying to reserve complexity for things that I actually care about. And all of that just to optimize the boot sequence is not important right at this moment, especially to do as the first thing. And so as a first thing, I will just do a slower thing. Well, maybe to do this slows down boot. We can optimize it by, can we optimize it by doing it lazily, e.g. tasks unmap their own guard pages, but then there is also a bitmap that checks if a guard page has been unmapped or not. Okay, so that's the to do, but we're not going to do that. So what we will do instead is pretty much, so the idea is to exhaust the pool. So the idea is just to allocate every single page and then unmap, and then we need to release them all back. And so how do we do that? I mean, so the naive way, what's the naive way? The naive way is I want to have some kind of, snooze the inline suggestions, have some vector container to store the pointers while the pool is not empty. Alloc process and store pointer in vec. At the end, release them all and check, and I don't know, assert check that the pool has full capacity or something like this. That is my current thinking. So, and it's going to be a task stack pointer. Okay, num tasks. And I'll just call it pointers. All right, what's up with task stack? Okay, so we got our ETL vector, right? And so that's this container. It's this full kind of large thing. And so also to do a problem, this might potentially get very, very large to allocate on the stack. That's a problem. So maybe let me think it through a bit more clearly. The reason I had this original approach is because if we, let's say I just like allocate it, process it, and then release it, the next time I go to allocate, I'll just get the same one. I'll just get the same one. And so I need to be actively holding this one in order to force the pool to give me the next one. And which is going to mean I need to eventually be holding all of them, which is going to just consume memory to store all of these pointers to task stacks. So that's a bit of a bummer. I mean, there are probably ways to optimize it, but they get a little bit more sketchy. So I guess the same process, like how do I do this? Like one, use a vector to yeah, the simplest place, use a vector to hold things and then release all of them. The con is this vector grows very large and is also stack allocated because ETL vector is like the type that I have for this. Unless I also want to statically allocate that vector. Ooh, that's an interesting. That is interesting. So I can make this a static, which is kind of not good, but solves the stack problem. But then also causes another problem where it just like wastes a bunch of memory for no reason, like really especially no reason. So call that 1.5 alloc as a static, or I guess it doesn't really matter, static allocate vec either via function or as member, but this has a big con. This has a massive con of this really wastes memory that is only used for a boot and then never again. So it's not amazing. And then this is a little bit sketchy, but can assume things about the layout of the pool, e.g. assume that the pool is contiguous and so e.g. compute start, store start pointer to the pool, and then manually assume that every element is e.g. size of task stack away and try to raw iterate over memory. This is a really sketchy idea. This is really sketchy and probably wrong and makes assumptions about ETL internals and is super brittle. So, yeah, that's a bit of a bummer. So this is actually a reason. This is actually, I mean, a con. Weirdly hard to store a vec of all to exhaust the pool in a memory efficient way. Maybe I'm missing something, but that is my understanding. It's like, okay, got this pool, get the first one. In order to guarantee that we'd never get the first one back again and just forever, we need to be holding it. So we need to eventually be holding like all these things. So, and that is consuming memory. So that's a bummer, and it's especially a bummer because in the kernel context, you don't want to use a lot of stack because stacks are kind of small to be efficient and leave room for user space. And I actually don't even really know what stack is running at this point. It's like the boot, it's like the really early boot stack from Limini, I guess. So it's just bad form to declare such big things on the stack and like, just like, let's say we have 4,000 tasks. That's like 32 kilobytes, right? Now what am I doing? What, 4,000? Yeah, times 8. Yeah. Like 31 kilobytes of memory on the stack just for this stupid vector, because these pointers are 8 bytes long. Also embarrassing that I need to use the calculator to do that math. So that is kind of bad. I mean, that's that at that point that sort of crosses a line for me. You know, I was kind of convinced by the simplicity argument, but it doesn't feel like a really like a viable solution. It's just setting us up for like it's just setting us up for problems in the future, and not even in like the far future. And like eventually I will pretty soon want to really increase this number from 4 to like a much larger number. And so doing this way would be like a super temporary hack, and I think it sort of crosses a line for me. So that's interesting. Yeah, the other idea, which I have been avoiding, no, over here, actually add a dynamic memory allocator, lol. Which I have been avoiding. Maybe there's a way. Okay, so traditional arbitrary length dynamic memory allocator. Maybe there's another weird way to do it. Maybe there's a way I could expose a way to alloc arbitrary physical memory in place construct an ETL data structure and then you use it as the allocator and then release the phys memory, which is an interesting variation on the theme of a memory allocator. It's like rather than exposing a malloc interface, I dynamically allocate one of these static containers. Which requires some kind of memory allocator. I mean, I don't have very much in the way of that right now, but I do have my physical memory allocator. But I basically want to say something like okay. All right, let's peek. What is the So that's the naive solution, but I don't think it works. Because this thing is commented out. Oh, wow, I get some... And so then... Wait a sec, what? So this thing, it's saying it just consumes everything. But then it forgets the task stack, so it has no way to free it later. So that's actually not a solution. I mean, it would be a solution if we could push back the pointer, but we can't. We just don't have a good way to do that. So I think just the sketchy idea is like, let's say we had, well, yeah, we don't want to statically allocate this thing on the stack. We want to statically allocate it on the heap, on some kind of heap. And so let's say we can get a fizz malloc, and it'll be the size of this type or something like that. So this doesn't exist. I don't have this yet, but we're trying to round it up to k page size. Yeah, I don't even have I think my round up whatever. And so we're gonna get a physical memory allocation for that much physical memory, and then we can get its virtual address in the fizz map, for example. Again, kind of a sketchy thing. We can get a physical contiguous malloc, just range of physical memory. We get its virtual address from the fizz map, and then we would like in place construct the pointers thing in there. It's like new I almost don't even know the syntax for it, but you know, I know you can do it. Something weird like that. You can in place construct and pass a pointer where you want the object to go, and then we could use this thing. Then we could do this strategy. But wow, that's like that's a whole deal. It also requires this part, which I don't have right now. It requires some way of allocating a certain amount of contiguous physical memory, which is not necessarily that hard. Oh, okay, because I have my bitmap frame allocator, and so all it really is, and it's as the hard-coded size, all it really is searching through the bitmap to find a certain amount of like either free ones or free zeros. Okay, what's the policy? Default everything to used. Okay, there's this thing where we are based off of the we init the bit set, which is where we loop over every usable region and init that, and we set each of these things to free, which means setting it to 1. So we need to look for a stream of 1s in the bitmap. That's as long as necessary. Okay, I mean, I wasn't planning on doing that today, but that sounds kind of interesting and kind of like a weirdly cool idea, actually, to work around this problem. So I'm considering it. It's either that, really. It's yeah, like this is not really an option. This is the one option. This is not really an option. This is not really an option. This is not really an option. It's either that way or just keeping it in the CTOR, or doing that this way of having the separate bitmap on the side, which frankly is simpler than this whole rigmarole of like dynamically allocating an ETL vector and using it temporarily. There's also the argument that this bitmap slightly will be a waste of space after a certain amount of time, but it's just a bitmap, so it should be pretty space optimized. So, I mean, okay, so just some basic math practice. Let's say we have 4,000. Yeah, I mean 4,000 divided by 8, 500 bytes of memory. So half a kilobyte of bits to track this kind of thing. So, I mean, any way you put it, like, yeah, it's 500 bytes of memory just lying around forever. So what's the call, I guess? I still think from an architectural level, I don't love having to do this. I don't really love that a task is aware of that. So maybe I can split the difference. Maybe the task, maybe there's some intermediate option. For bit set on the side that the task CTOR checks of this. So still do it lazily, but not in the task CTOR. Make the scheduler responsible. So the idea would be to get the benefits of doing it lazily, but also get the benefits of not having this code be here in the task, which means the code would be over here. And wait, isn't it? Init task is just never used. This still unused. Create task. Yeah, so the idea would be to make the scheduler responsible for this. So but actually this is like kind of strange also, because once you allocate something from the pool, there isn't really a notion of an index into the pool. That's not something you can query. So, and that breaks the idea, because the idea would be like, okay, this task is got a stack. It goes and checks, okay, like, let me see. Let me get the index of this stack, and let me check if it was initialized or not. But it's that idea, like there's no concept of an index of a task stack. So that's also kind of cooked, like that's also kind of a busted way to go about this, actually. Nope, no way to get the index of a task stack in the pool. So all of these ideas are kind of collapsing a little bit. I was just trying to clean up a little thing, and all of these ideas are kind of collapsing. Which kind of brings us back to number one and the sub-solutions for number one. None of them really are like really super viable or pleasant. This is the best of the options. And I don't know if it's great, but it's kind of a fun idea, and it might be fun to try to like stunt program this at least. The idea of dynamically allocating in place the ETL static vector is quite a quirky idea. But it's not, but it's not wasted time because it will be necessary to have more advanced memory allocation functionality at some point. And like even just the ability to allocate a range of memory, which is currently not even possible. It's only possible to allocate on a page basis. And so let's see, let's try it out. So we need this sort of like like this contiguous like allocation kind of thing. And the question is, where does it go? Does it go into this class or what? Maybe? Interesting. I don't know what it would be, but like alloc range something. There's also sort of this issue of like this thing is yeah, this virtual function kind of stuff for the testability of like other random stuff. Because now we are in kernel lib with the generic code. It's not going to be void, obviously, but alloc contiguous. Alloc fizz contiguous. And then like size t. Frames. It's interesting. And I think I want to introduce some concept of like a fizz range or something like that. There's gonna be this fizz range thing. And what is a fizz range? Oh my gosh. Has a base address and then a size, which approximately, it's like a fizz, yeah, I don't know, fizz, yeah. Almost like a weird kind of span or something. Not really, because it's not a span, it's like a view over a container, but this is like some weird function that returns this new concept of a fizz range. Then we could also have like maybe they would could free a range, something weird like that. But this needs to be an optional because it can fail. Yeah. So that's kind of the idea. And if we had that, then we could use that. And so it would be something like O range equals M frame like something like let me whoa. Task stack.
Let me see math.hpp. Round up. Okay. Round up. Wait, let me. What is? So we're getting the size of, rounding it up, and we're dividing that. So let me see. So the way it's like, this is a num frames. It's not the number of, it's not the amount of memory, it's the number of frames. Maybe that's inconvenient. Maybe it's better to just let clients pass in the size. In which case we just, but then that allows the clients to pass in non-contiguous. I don't know. Maybe it's easier to force everyone to just get page size. So we're allocating a physical contiguous chunk of physical memory, and we get the phys range. And right, that's the size of this type rounded up to page size divided by the page size. Okay, and then we can assert, and then you can bitmap adder converter on the base, and then it knows what we want to do. Then we in place construct the vector here, and now we have access to it. And then now we can, while, okay, yeah, it's going crazy. Man, it's while, yeah, mtask stack pool, not empty. We're going to dot create. Going to pters dot push back p task stack. To guard page dot data. And what's the problem here? Do I need to subvert adder? What? Okay. How did I do this over here? I casted it, of course. Okay. So, oh my gosh. uint 664t. Again, don't do this at home. Reinterpret cast. All right. What am I saying? Reinterpret cast. All right. Be a good example. Maybe there's a better way. This is so wordy. No, it's kind of unfortunate that the vert adder just, it's only convertible. What if I add a conversion from void star? Is that okay? That would be nice to have, because then we wouldn't need any of this. I think we could just go with this. Unmap it, then push it back. So for every, while the pool is not empty, we're going to create something, unmap it, push it back. Either inval page after every single one, or reload the tuple altogether, and then now we can, for auto task stack in pointers dot release task stack. That's what? Oh, yes, I did. Wow, interesting. Yeah. Yeah, that's interesting. Not so common that I do that. So do that kind of thing. So yeah, let me release it all back. And that's sort of the idea. And it mostly now hinges on having this function be implemented. Which we can try to do. I'll start with add definition. Did it add it in the header? Why did it do that? There is a perfectly good. Perfectly good. I'm just sketching this out right here. Okay, add definition. Why does it do that? Okay. Okay, I think this is a bit of the easier one. So just to start off with, so the fizz range is the p-adder and num range. So actually, what does the num frames mean? Or would it be better to store a base and an end? Start and end, is that a bit more idiomatic and maybe even easier? So auto p equals range dot start, and then yeah, we just need to bump the pointer every page size and call release. It's yeah, so yeah, I'll let it do its thing. Yeah, it's pretty much this. Yep, so God, it's such bad practice. Such bad practice to allow myself to become reliant on the AI. So can't really do very much. This is sort of like current equals fizz adder current value plus k page size. It's not really supported to like bump it. So maybe there's some ways to use like a stud views or something on that. Like I think the stud iota, something, but not so important. And then lastly for this thing, and so for this thing we also need a kind of a cursor, and so we have this bit set. We need to like look through it for a range of ones, of a certain number of ones. And if we find it, we can return. And so we're gonna need, I think we're gonna need like 2 cursors, like this first main cursor, we're gonna plop it down. Then we're gonna kind of start checking how many ones we can get. And then, yeah, I'm just gonna start with that. So size T. Main cursor. What am I doing? Second cursor, something weird like this. And so what I want to do is I want to find the first one. And so I think there's like some ways to do that. And so find first set. Right. It's the main. It's going to be initialized to and then we're going to just like have this like sort of loop where we're going to count, like kind of count and see how far we can get. I feel like some kind of helper function will be good here. So I'm going to make a private function called try range or something like this. I don't know. And I mean, it would be good to have some unit tests, to be honest. Maybe I can have the AI help me do that. Test bitmap, bring allocator. Please generate a few basic unit tests in. I don't really know why I'm not using Copilot or whatever in the, here I'm using Cloud Code, but in for, oh, this is stupid. I should use the coding agent over here. Please generate a few basic unit tests for and using Sonnet, okay. So the idea with the unit test is I want to set up like some basic bitmaps with a couple bits here, a couple bits there. And I can do that using the memory map. And then I want to just try to do some allocations that will either succeed or fail. Like, yeah, like, fill up all memory or fill up a lot of memory and then try to do a big allocation that won't fit, that should fail. Or just, you know, have a big chunk of memory at the start, try to do it and then verify that it can find it. So it should be pretty good at that. And so if there's no memory available at all, then this thing returns null opt. Single frame. So we allocate, we like mark I forget how much that really is, from hex 2000 to it's, I need to climb the host. Okay. So it's this vector of these things, which is the base, length, and type. Okay. So base at 2000, length 4000, and nice. That's kind of cool. We can check that. If you want one thing, this is what it looks like. And we allocated 4,000 4 pages, and so there should be 3 free frames. Cool. Now it's checking multiple frames from contiguous region. It's kind of similar to this one, but just multiple frames. Returns null opt when not enough contiguous frames. Yeah, so this case, there are these 2 sections that each have 2 pages. We want 4 pages, and this cannot be supported. So cool. Then free arrange a single frame. And you get it back. Cool. Free multiple frames. Okay, then next sort of like a round trip alloc contiguous then free contiguous, and then it gets back. So that's pretty solid, and that will allow us to TDD this a little bit. All right. So I feel like I want a function that's just sort of like, give an attempt, sort of like try a range, and it's given a start and a size t num frames to try to get. Yeah, so we have all these bits. We're in starting position, just try to do it at this position and see if it will work. And if it does, return that back. Otherwise, return that it didn't work. And then from the outside, we can just have some kind of like driver loop that sort of just drives it. That's sort of what I'm thinking. So the start frame and num frames. And so the idea is, and so we want at the start frame, we want them all to be ones basically. And so for int I, okay. So line suggestions. That equals 0. I is less than equal to num frames. Interesting that I chose an int because size t. I'll just do this to keep the peace. And then here's the idea. It's like, okay, we just want to test each. So these are the offsets, right? Right, and so then we need, so our candidate is just to be kind of verbose, candidate equals start frame plus I. And then if is free candidate, cool, we keep going basically. And so if it's not free, at any point in this list, we want to return the null opt, just to appease. That's wrong. Obviously, we need to return some fizz range of some kind, but that squiggly was there. And so basically, the idea is like, okay, we're just doing kind of, we're launching one attempt. We're just iterating over all these things. And we're just trying, okay, is it free? Is it free? Is it free? Is it free? And if any of them is not free, we stop. If we got to here, they're all free. And so we can return the fizz range being start frame and start frame plus num frames. But that's not right. It's this thing. Page is to be. we want to compute the end address, right? Do I have helpers for this memory types? No, I don't think so. Okay, so what? I don't. So let's say we have hex 4000 and it was 2 frames, 2 num frames. We want hex 6000. So we need to add 2000. So oh, it's not cage page size, it's page bits. Good warning. Okay. So that's my but I didn't do it right because I didn't actually allocate anything. So the idea is like, okay, I don't know, let's just do some random, and the ones are the free. And so let's say we're looking for 2, and so and this is our start frame. Wait, this is like confusing. What is start frame? Start frame is an index. It's not an actual frame number, which means that this thing also needs to be k page bits to convert these. Frame, and I have this helper, frame adder. Yes, so frame adder, and the inline suggestions are back. Okay, how's this looking? Still wrong, because so now it's like, let's say it's 0, 1, 2. Start frame index is like 2, and we're looking for 2 frames. So we're gonna iterate twice. It's like, check this one, okay, it's free. Check this one is free, okay, cool. And now it's time to actually allocate all of them. And so now we can go here and mark used candidate. Allocate all actually test. Do we have a contiguous range? Yes. Okay. We allocate the range, and then we can return that we did that. And so let's just say we were at 0, looking for 2, and what's going to happen, we're going to get 0 plus 0. If it's not free, return null opt. So we're just going to, if you see this not free, we just return immediately. And so we only end up returning if we get the start right, and then all of those bits were free. I want 5 free bits. Yeah, okay, so then we just loop through all of them, kind of get them. Or we could, but the thing is, yeah, the question is like, the purpose of this loop is not really to modify anything. We're just sort of doing a pre-flight just to see if it would be possible. And only then do we want to mark things. We don't want to be like allocating things as we go, and then just to realize that there's not enough room. So I think this is the way to do it. And then let's see, assuming that is kind of correct, we can try to use this. And so now we need a driver loop that's sort of like some kind of loop, and it's going to be something along the lines of AutoX try range. I guess we don't need the second cursor anymore. It's really just this main cursor. Main cursor num frames. Right, that's how the API works. And we get the O range. And the kind of interesting thing here is there could be potentially these massive spans of zeros. And so we want to sort of be kind of fast and find the first one quickly. And so that's what this find first set thing is for. But this function literally, does ETL have a bit set? ETL does have a bit set, and I don't know, I didn't use it for some reason. Right, I mean, I'm sort of thinking optimizations at this point, but it would be nice to sort of zoom through these zeros and only start at these 1 points. Anyway, the naive implementation. Okay, let's just say naive implementation is this. And so I don't know what the condition is quite yet, but we're going to try the range with the main cursor, and let's just say it's 0. Again, naive implementation. But I think a pretty simple optimization is just to default it to the find first. I mean, that's simple enough where we can just go and cut and keep it, I think. And this thing returns, okay, we got this thing returns a -1 in case it couldn't find it. So I'm going to assert main cursor. But okay, here's the plot twist. Oh, this is interesting. So plot twist, and so static cast, something like that. Okay. Suggestions. So we're going to just give it a try at some place, and then here's the thing: if okay, snooze and let suggestions for 5 minutes. If we got something back, then it like worked, and so I think we can return the. It's very intimidating seeing that AI just generate a bunch of code when I didn't necessarily think it was necessary. So I hadn't gotten that far yet. So going to try a range, and then if it found a range at this place, like that's amazing. And I think we're kind of done at that point. I mean, if you, like all that really is necessary to do is mark used to mark something that's allocated, and so this thing is doing that already. So then the question is just like what happens next, and so I think we do need. So then we need to set main cursor to something. I think that's the question. What do we set it to? And we just set it to the next thing to try, basically. And so it's sor plus num frames. Okay, but there's a couple problems, I guess. And so what happens at the very end of things if we sort of run off the end? That is an edge case. I wasn't quite thinking of And so we're going to need to handle it either here or in the other thing. Maybe we can handle it here. Maybe we only try a range. Maybe we only try a range if we're sure there's even enough bits set. And so space left equals m bit set dot size minus main cursor. So let's even make this a bit simpler. So let's say we have I think we have 4 bits, and the bit set is as 4. We're here, so we're going to subtract the 2, and so that gives us so main cursor is an index, right? This is kind of confusing. Current frame index. And so we got an index. And so let's say we're at index 1, there's 4 things, there's 3 left. So that's the space left. Again, these names probably can get improved later. And then so if num frames is greater than space left, so like space left is 3, we're looking for 4. There's no way we can satisfy that, and so we return std null opt. And there's some warnings here. Let's type, this kind of stuff. Also, do it that way over here too. Okay, so we're going to be checking up front. We could then consider adding an assertion in the other helper function. But maybe for now we just go with this. And so the idea is like, okay, on every iteration of whatever loop this is going to be, we check if it's even possible based off of the current state of where we're at and given how many we're looking for. And then if there is, we go and do an attempt. And we're like, okay, give this position, just try to go for it. And then it's going to say, okay, I got it, which means we return. Otherwise, we want to bump along and keep trying. So that's kind of an interesting case. Let's say we're trying to get the naive solution is we just try every single bit. But that doesn't make any sense. Like if we're here and we know it wasn't possible in the next few, I guess we don't know the reason why that isn't true. Like let's say we're here and we're looking for 3. Okay, didn't find it. So it's actually not correct. What I wrote is not correct. Because let's say we're here and we're looking for 3. If we jump all the way over here, that's going to miss an opportunity right here. And so to really be thorough, we need to just go and try every bit, actually, I think. Up until the very end. So this is going to handle our case at the end at some point. This is going to eject us from the loop. And this is going to eject us from the loop if we ever find something. So I almost feel like optimize zoom to find the next one. So I almost feel like this is a minimal version. I'm taking breaks. Take 20 seconds. Okay. Okay, let's give this a code review. I probably made some mistakes, so I'm just gonna, as always. So we're gonna initialize the current frame index to the first set. I'm gonna zoom over to the first one. We're gonna check, like, it's kind of interesting. Let's just say it looks like this. We're gonna zoom over to the first one. I guess we're currently asserting. We could even, which is actually not really, that's actually not correct to assert here. It's with the place of the client code to assert on that. We should just bail out if less than 0 turn. Good. Okay. So now let's see. So we're gonna zoom over to the first one per this. And then we will launch into the loop. And we're just gonna check if there's even space left. And so yeah, so if based off of any particular position here, it's going to give us this, and that's our space left, the size, you know. Yep, space left. And if the number of frames is greater than space left, what if it's equal to? Like, what if it's equal? So we're at 2, and we got 2 space left. Looking for 2, so that's actually valid. Yep, and then this. Yep, and so we're just doing that check, and then we go ahead and launch an attempt at current frame index at that 2 4 frames, and we get an optional. If it found something, that means we found it and locked it in. Try contiguous. Try alloc. Oops. Try alloc contiguous. Or maybe even alloc. No, this thing is already called alloc is contiguous. Try alloc contiguous sub range. There we go. Maybe even try is not necessary. Contiguous subrange. Helper function. Okay, so yeah, so then right. If we launch in return. Otherwise, we just take wherever we were at and bump it one more. And what if this thing is 0? Like, Frames equals 0. I'm just gonna return null opt. I mean, I could even just make that clear if num frames 0. Just do that super upfront as a separate thing. But then, what if we're looking for one thing and get to the very, very end? What happens then? So, you know, if we're looking for like 2, get over here, that's gonna bail out. What if we're looking for 1? Then let's say we just don't find it. Let's just say we're just like all the way over here. We're looking for one thing. I mean, this thing will find it here, I guess. But let's say we're looking for only looking for 1, and then we'll bail out initially. And if there was nothing, they will bail out initially. If there was 1, we'll, yeah, and it's like here we'll just like get it. So I'm just thinking about the case where it gets all the way like really to the end. But in that case, it's going to be handled because the space left check is going to get it. And if we're really only looking for 1, then it must have, yeah. There's no way to end up at the very end and be looking for 1 here. Because we would have bailed out initially or would have found it, so yeah. So I think it's looking okay to me. Let's see if it compiles. Part that didn't compile is over here. Fizz range start value. No. There we go. Oh, and this thing is like struggling to compile or whatever. Let me see. So I don't know. Like then, this one. What bugs do I have over here? So we're starting. Just do some basic 0 to blah. The candidate. Is it not free? Bam. Otherwise, it's free, and we just keep moving until we find that many free ones. We get them all. I'm just doing that. So I don't know. This is gonna be super embarrassing probably, but I'm just gonna run the unit tests. And they all passed. What? Was that on the first? No, were they even running? They're probably not even running. Whoa. Chad, did I get that on the first try? Did I land that on the first try? On camera? That's what? Yo. All right. I was super, you know, it's always so easy to have bugs, so. And I even was disabling the AI chat companion. So, so that, yeah, that was my best shot at just trying to do that. Seems to be working somewhat well. I still almost don't even believe it, but tests are failing if I comment out lines here. So what other lines can I comment out? This will probably infinite loop if I don't do that. If I Okay, I'm happy. That's a win. I'm gonna call that a win. Dubs in the chat. Dubs in the comments, please. If you're watching this and see this, please drop a dub in the comments. I'm proud of that. Okay. So now we're gonna pop over back here into kernel world. And re-engage the playing D. And now the idea is that this thing works. That was a very long way to just sort of get rid of this whole thing. I want to add some comments. Or log. Okay. What were we gonna do? Assert? All right, we can do that too. Let's get the log. I just want to see this in action. And then, of course, we need to remember to free. There we go. Check it out. Okay. That's our first form of this weird hybrid of static and dynamic memory allocation, where I dynamically allocate a range to put a static allocator into it, use it, and then deallocate. So I don't know, I'm just going to run the kernel, and then that's going to be, I'm going to call it, it's kind of late. Okay, my assertion failed, but that's expected because I was exiting the idle task. So let's okay. Some kind of bug is here. Wow, that's fascinating. This thing should be getting called. Has value true. What? Okay, I got something very basic wrong. What? Okay. Capacity. What? Oh, wait, what? Did I, it's empty. Oh, wait, did I? It's not good. Not full. Wait, what? Wait, the capacity is 4 and empty is 1? It's empty right now? It's an empty pool, meaning nothing has been taken out of it? All right, what? Returns true if there are no allocated objects in the pool. Available free objects. So allocated objects and freed objects. So when you allocate something, you kind of sort of like push something into the pool almost, something weird like that. So it's like, while it's not full, I guess, is what we want here. So, and also check it out. These prints happen super early on. They happen before, and this is interesting. This is quite early in the boot process because this is even before the kernel's constructor runs. This is because the scheduler is part of the kernel, and so this runs even before we dump the memory map. That's kind of cool. That's super early in the boot process, and we got these 4 prints. And to test the whole point of doing this, what I could do, I don't know, like I don't know how much stack room there is, but yeah, I don't exactly know how much space is left on the boot stack, which is where this runs. But the whole point of doing that sort of convoluted thing was to pave the way for radically increasing this number to 4,000, which is going to cause kind of a lot of memory to be allocated. I mean, 32K approximately, 4,000 8-byte pointers, 32K of memory to store this vector for tracking the guard pages. So that is kind of a lot. I mean, that's a lot. So I don't know what if I could just run the kernel. Interesting. Okay, it's boot looping. So clearly, clearly there's some weirdly it gets here and then, okay, I don't know, that'll be a mystery for next time. I don't know why that does that. So I guess that'll be a mystery for next time. But conceptually, I don't know, conceptually it was kind of working, at least for the small numbers. So we'll figure out whatever bug it is with the big numbers later. All right, that's gonna be, well, it's kind of a longer stream than I planned. That's gonna be it for today. Y'all, thank you very much for watching. If you like this content, please subscribe to my YouTube channel, and I'll see you next week. Peace.